Good morning, guys. I'm sure that you have been anxiously awaiting the return of statistics into your lives. I know that at the end of the week during spring break, several of you started to get re-engaged already, and were sending me a few questions. So I hope that you guys are ready to finish out this semester. We're going to have to talk about a few things when we have our next Zoom class, and I'll send that schedule out later today for the remainder of this week. There won't be a live meeting today. We're just going to try to start getting our feet wet. But unless you guys have some questions that you want to address, then we'll definitely take those questions and get you guys rolling. But no live class today on Zoom, but we will have two later on this week. So what we're talking about now are the sampling distribution of the sample mean. And what we're doing is, so we're taking samples and of various sizes, and we're computing the mean of each one of those samples. And then we're going to look at what the distribution is of that mean of each individual sample. So let's just say, for example, there are 24 of you in class, and I wanted to do samples of 2 students based on, I don't know, we'll say height. So if I pick at random 2 students, I would take those 2 heights, add them together, take the average. That's the sample mean. But what I would do is I would do several samples. So then I would take 2 more students and do the same thing. So then I have this list of sample means, and they vary from from sample to sample. Obviously, we've seen that in previous examples, specifically the one where we talked about the height of the 5 basketball players for the Lakers. So we take these sample means, and if we plotted them, we would see that it should be normally distributed. And we're going to talk about that as we go through these notes. So I'm going to go ahead and we're going to start right here looking at the first steps and then the first couple of examples on the sampling distribution of the sample mean. So we know that let me get my pen going here. We know that the mean or the average for X bar, which is our sample mean, is the same as the mean for our entire population. So the sample size mean and the population mean are equivalent. However, the standard deviation for X bar, which is our sample mean, so let me just make a note here for you. X bar is the sample mean, in case you've forgotten that. Okay, so we have mu sub X bar is equal to mu, which means, like we said, that the sample mean, the average of the sample means is equal to the average of the population. Sigma sub X bar is equal to sigma divided by the square root of n. So that is the standard deviation of our sample means is equal to the standard deviation of the population divided by the square root of our sample size. And let's just go ahead and look at our first example where we're talking about IQs. The IQ is measured on the Stanford revision of the Binet-Simon intelligence scale. They are normally distributed with a mean of 100 and a standard deviation of 16. For a sample size of 4, use simulation to make plausible the fact that X bar is normally distributed. Again, recall X bar is our sample mean. So I've gone ahead, instead of watching me type all this out, I've gone ahead and done that. Here in these first 4 columns are my samples. Each column has 1,000 samples in it, so this represents my samples of 4 people randomly chosen from the population. And then in this column, I have taken the average of the 4 values immediately to the left. So all the way down, I have all these sample means for the 4 individuals randomly generated by the function in Google Sheets. And then what that gives us is this distribution where we have a histogram, and you can see looking at that histogram, and that's just the histogram of the sample means only. We see that this is approximately normally distributed, which is what we would have expected, or actually what we would have hoped for, because we are normalizing this variable by just looking at the sample means. If you need further help on generating something like this, please ask me. We have done these before. All I've done here is simply taken what we've done before using just one column, and I've expanded that out to extend across 4 columns, and then I've taken the mean of those 4 columns to generate the sample mean set. So the histogram here shows that this is approximately normally distributed across the sample means. You can see that it is centered around 100, which is the mean of the population, and it's the mean of our sample distribution. And then it's just distributed in this normal variation where we have the peak at the middle around 100, and then it tapers off to the left and to the right, just like you would see in the normal standard curve. With example 2, here we're talking about the standard deviation again of a normally distributed variable. That's in the red box there at the top of the screen. But example 2, it's just saying consider again the variable IQ, which is normally distributed with a mean of 100 and a standard deviation of 16. Obtain the sampling distribution of the sample mean for samples of size 4 and 16 respectively. So let's look at part A. We know in part A that mu sub x bar is equal to the population mean. So we know that our mean is going to be 4 of our sample sizes of size. Oh, sorry. I don't know why I wrote 4. I was looking at the wrong thing. Our mean is 100. So our mean of all of our samples should be 100 because the mean of our population is 100. The only thing we have left to calculate now is sigma sub x bar, which is our standard deviation, and that equation is given above, where it's just sigma sub x bar is equal to sigma divided by square root of n, where sigma is our population standard deviation. So in this case, we have a population standard deviation of 16, a sample size of 4, and that's going to give us 16 over 2, which is equal to 8. So we have a result here that mu sub x bar is equal to 100 and sigma sub x bar is equal to 8. We'll interpret both of these simultaneously. So I'm going to go ahead and do the same calculations on part B. We have mu sub x bar is equal to mu, which is still 100. And then we have sigma sub x bar is equal to sigma over square root of n, which is going to give us 16 over square root of 16. And we end up with 4. So our values here, mu sub x bar is still 100, and sigma sub x bar is 4. So what this is telling us is that sample sizes of 4 in part A, we would have the same mean of 100, and our spread is going to be 8 IQ points, our standard deviation. And then with part B, when we have 16 people in our sample, our mean is still 100, but now our spread is slightly smaller. It's at 4. And so what we're noticing here is a trend. The larger our sample size is, the less our spread is going to be, the closer it's going to be to the true normal distributed values from the overall population. So here in part A, our sample size is 4 and our standard deviation is 8. For part B, our sample size is 16, which is a larger sample, and our standard deviation is now 4. So our standard deviation did decrease the larger our sample became. The central limit theorem. The central limit theorem, this is probably the first theorem I believe that we've come across in this class. It just simply states that for a relatively large sample size, the variable x bar is approximately normally distributed regardless of the distribution of the variable under consideration. The approximation becomes better with increasing sample size. So in our first 2 examples, we were looking at IQ, and IQ is a normally distributed variable. So in turn, our x bar, our sample distribution, should also be normally distributed. But what the central limit theorem says is that if we take a large sample size, And when we say relatively large, that really is kind of a generic term. What it really is, what do you define to be large? But anyway, what this is saying is that if we take any sample of any variable, the means of all the samples should be normally distributed. And then that improves the larger our sample size becomes. And hopefully this next example will kind of help clarify that. When we are talking about relatively large, though, what I would like for you guys to consider is right here we're talking about typically 30 or more is the size of our sample. With example 3, we're talking about population of U.S. households. So it says, according to the U.S. Census Bureau, a frequency distribution for the number of people in the United States is given. The frequencies are in millions of households. So here the variable is household size, and the population is all U.S. households. From the table, we can calculate the mean household size to be mu is equal to 2.5 persons, and the standard deviation is 1.4 persons. The figure provided is a relative frequency distribution. That's what you see here on the right in purple. So using that data that's provided in the table. And it says, note that the household size is far from being normally distributed, is certainly right skewed. Nonetheless, according to the central limit theorem, the sampling distribution of the sample mean can be approximated by a normal distribution when that sample size is relatively large. Use simulation to make that fact plausible for a sample of size 30. So here's our relative frequency distribution on the left, this table you see here. And then on the right is just the graphical representation. It's the distribution based off the data provided in that chart. So you can see here with one person in the household, the frequency is slightly over 30 million. With 2 people in the household, the frequency approaches 40 million, and that's what we see in our table. So these are just visual representations that will help us understand what we're going to look at on the spreadsheet. So with the spreadsheet, and there's a reason why I did these in advance, is because what you don't see is to the left of this, I have, this actually ends up being samples of 24 rather than 30. But I've done 1,000 samples of 24 people, or 24 samples, and I've computed all the sample means in this column here in. And the reason that I did not do this in real time to show you guys is because it takes a little bit of computing power. It ran for about a minute and a half, I believe, to compute everything, to generate the samples. So sometimes when we do some of these things, it will bog your system down a little bit. But I don't believe that I ask you guys to do anything that extensive in any of the homework problems. So again, column in here is the sample mean. So I've taken each one of these rows and I've computed the mean of every row, and I've generated the sample means for the 24 samples, or the samples of size 24. And here is the histogram of those sample means. So if we look at this graph, you can see that this graph does appear to be normally distributed. And when we look at our original relative frequency distribution, you can see that this is definitely going to be a right skewed graph. It is not normally distributed. However, when we normalize the variable, or when we compute the sample means, we do come up with a normally distributed X bar, which is our sample mean set. And here is, I don't know why that says note S, but I guess I wasn't paying attention when I typed, but that should say the sampling distribution of the sample mean. So suppose that's where that S goes. This S goes in front of here. So that should say, suppose that a variable of a population has a mean mu and a standard deviation sigma. Then for samples of size n, the mean of X bar is equal to the population mean. The standard deviation of X bar is given by sigma sub X bar is equal to the population standard deviation divided by the square root of the sample size. If X is normally distributed, so is X bar, regardless of the sample size. So that goes back to our IQs, because IQs are normally distributed. if the sample size is large and X bar is approximately normally distributed, or if the sample size is large, X bar is going to be approximately normally distributed regardless of the distribution of X. And we're going to see this now with example 4, and this will be the last example before the conclusion of these notes. So here we have the National Center for Health Statistics publishes information about birth weights in vital statistics of the United States. According to that document, birth weights of male babies have a standard deviation of 1.3 pounds. So we have a sigma of 1.33 pounds. Determine the percentage of all samples of 400 male babies that have mean birth weights within 0.125 pounds of the population mean birth weight. Interpret your answer in terms of sampling error. Okay, so we need to first come up with the fact that we're not given the population mean, but we do know that mu sub X bar is equal to mu. So we can go from here and we can calculate our sigma sub X bar is going to be equal to 1.33 divided by the square root of 400, because that's our sample size. So we get 1.33 divided by 20, and that's going to be approximately equal to 0.0665. We can take the sample standard deviation and use this to compute our z-scores. So again, remember, we don't know what the population mean is, but we do know that we want our weights to be within 0.125 pounds of the population mean birth weight. So let me just sketch a quick drawing here. What we have, if we have this normal curve, our mean is right here, and we want to calculate to the right of that, so that's mu plus 0.125, and then to the left of that is mu minus 0.125. So we're going to use these two interpretations in our calculation to come up with the z-scores. So for the first one, if we are looking to the left of the mean, of the population mean, we have z is equal to mu minus 0.125 minus mu. That's our standard notation. This is our sample, and then this is our population. So this is something that we've done before. We're just introducing a new way to calculate it, divided by our standard deviation, which we're looking at the sample. So we divide it by 0.0665, and what we end up with is negative 0.125 over 0.0665, which is approximately equal to negative 1.88. We're going to do that again for the right-hand side. So looking to the right of the mean, and here we have z is equal to mu plus 0.125 minus mu over 0.0665, and that will simplify to 0.125 over 0.0665, which is approximately equal to positive 1.88. So again, going back to just a standard normal curve, we are looking for the area that lies between negative 1.88 and positive 1.88. So if we will go back to our z-table, you can find that the area under the standard normal curve between negative 1.88 and 1.88 is equal to, so we're taking this value minus this value I'm not going to go back to the z-table. Hopefully you guys know how to use that at this point. But when we take the z-score value for 1.88 minus the z-score value of negative 1.88, we get 0.9398, which means that approximately 94% of all male babies have a mean birth weight within 0.125 pounds of the population mean. There's your homework problems. Let's see. I want to make sure that I didn't lie to you and do a crazy sample size for you all to simulate. Doesn't look like I did. So I wasn't that mean. Okay, good. And there's only 4 questions. So again, I hope that this is not a tough reintroduction back into statistics. I also hope that you guys are doing very well, and I'm looking forward to talking to you later on this week. Again, please, if you have any questions, don't forget to just send me a message, and I'll be happy to answer them for you. You guys have a wonderful, wonderful day.